16A problems. Just because it says 16A does not mean for sure that there's going to be a 16B. I think we're going to be working with AP problems after this because I think they demonstrate a little bit better like how we can prepare you for the AP test. So for chapter 16, this is all about acids and bases, and of course we start off with the Arrhenius and Brownstedt-Lowry. There is actually a third. So Arrhenius was the first, and he talked about H plus and OH minus. Brownstedt-Lowry came in second. They talked about how proton gets donated by the acid and gets accepted by the base. And there is a third one that talks about pair of electrons. So that's the Lewis acid and Lewis base, but we won't get into that until later on, if at all, because that's a little bit more complicated and takes a little bit more work to figure out. So the first one's super easy, right? He's the pirate acid base guy. He says that if you increase the H plus, it's an Arrhenius acid. If you increase the concentration of OH minus, that it's an Arrhenius base. And this is actually a very limited view of what's going on between Arrhenius and Brownstedt-Lowry, because anything that increases the OH concentration would be considered a base then, which does allow for a wide variety of compounds, but it doesn't allow for all of those things of what's going on. Here's what I mean by that. You can have a situation where you are not increasing. You can have a situation where you are not increasing. This is not a great example. Let me make this just a little bit better here, where I do this. There. That makes this not a strong acid. That makes this okay. So let's move on. So here I have a situation where this species right here, the bisulfite polyatomic ion, accepts a proton like this and is now considered a Brownstedt-Lowry base because it accepts a proton. It accepts the hydrogen plus one from the hydrochloric acid. So this would be a Brownstedt-Lowry base. Notice that nothing on this side over here resembles an OH. So you don't have to have an OH for a Brownstedt-Lowry base. Now sure, if you increase the hydroxide ion, then you have accepted a proton from somewhere. You are a proton acceptor from one side to the other. So that is like also part of that's also part of what's going on. So like I said before in the notes, if you're Arrhenius, you look like this as far as a Venn diagram is concerned, but if you're Brownstedt-Lowry, then you encompass all of that and more. So that's what it looks like. Okay, let's move on. When ammonia is dissolved in water, it behaves both as an Arrhenius base and a Brownstedt-Lowry base. Explain. Well, so here's what we mean by that. So ammonia is added to water, so it looks like this. This is an equilibrium because, well, you'll see. In this situation, I get water donating a proton, so it actually becomes the acid in this scenario because it donates its proton to NH3, which turns into NH4 plus, which we know, and then we get OH minus. Okay, so here we're increasing the concentration of OH minus, which is why this is considered to be an Arrhenius base. However, notice that the OH did not come from NH3, which means that NH3 was a proton acceptor, which is why this is considered to be a Brownstedt-Lowry base. Okay, so actually I should put it on this side. Brownstedt-Lowry base on this side, and then the conjugate, it would be the conjugate acid, would be right here, NH4 with a plus. So base conjugate acid pair here, acid conjugate base here. That's it. That's why it's both Bronsted-Lowry and Arrhenius. Let's move on. The next one's going to be a little bit easier to do because all we have to do here for the conjugate acid is show what happens after we add an H plus to it. That's it. These are super easy. So what happens here? HCN is the conjugate acid for Cn minus as the base. So for each one of these, all I'm doing is adding an H plus. And then you can see what happens on the other side. So here I get H2, PO4 with a minus 1. Here, this is an interesting one because the H ends up on the outside here. This is something we need to get used to. Very oftentimes, when it's by itself, NH3 will increase to NH4. This should be common because you've seen this as ammonium. This is the only positive polyatomic ion that we use, that we've taught you about, that I've taught you about here in chemistry. And this one does exactly the same. So it's C2H5, except it doesn't jump up to 4. There's already one bond with the carbon here, so that means it jumps up to 3 with a plus 1. Okay, the 2, I covered that up. Just give me an eraser. So the 2 jumps up to a 3, and we add a plus charge because it's already neutral. That's it. Okay, those are the first two problems. Stay tuned for the next two.